Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing fan of flow, and most likely today will be the last class of fan of flow, and next class onwards we will talk about heat transfer. Okay. I will just recap quickly and then we will go to numerical example. Let us say I have a duct and we are starting with, let us say, m less than 1, m1 less than 1, the inlet, and I am going to say this is my duct length, and some length L, and for this Mach number m1 I am going to say that for that particular friction factor and the hydraulic diameter of my duct, the L star happens to be this long, L max or L star happens to be this long, and if I have only this length, then now I can say that my flow, since it started subsonic, is going to stay subsonic up to here, but it is going towards m equal to 1. From here it is going towards m equal to 1. Now we will look at it similar to the way we did the expansion fans, Prandtl-Meyer curves. I am going to say from m1 it is going to reach Mach number 1, and somewhere along the way it reaches m2. Okay. Now if I think about m2 as my starting point, then it will take exactly this length to reach this L star. So this length will be that particular L star for this exit Mach number m2 for this particular problem. Okay. That is the way I want to think about this. This is the way to solve the problem. Okay. I am going to say if this is my m2, then this is my L1 star, that is L max based on that f, that dh, and this Mach number m1, that is this length, and this will be my L2 star, which is for that f, for that dh, if I use m2 I will get this length. Now the difference happens to be the length that the flow takes to go from m1 to m2 till it reaches m equal to 1. This is the way I am going to think about this problem. Okay. This is one simple application. Now I will make the case a little more complicated. I will just say I extended the length up to some length only up to here, not past my L star. Then what will happen? I will consider this as an m3. If I start from m2 and think of this problem, it is a duct of this length, whatever this length is, L prime, let us say, then I will just add that to L prime here, L prime. I am now adding one more section of this pipe with the same f and same hydraulic diameter. I am adding one more section here. Then I can just think of this problem from m2 onwards as if it is the same as the previous problem, just 1 is replaced by 2 and 3 is replacing 2 here. Okay. That kind of a problem just coming around here, that is all it should be. I am going to think about, I am starting with m2, that will have a L2 star, and now I have a m3 such that if I go this extra length, that will become my L3 star. This is the way to think about this problem. So if I say this is the initial length, what is the Mach number, then if I add this much length to it, what will be the Mach number, that kind of a problem, then I will approach it this particular method. I am just going to find the L3 star, L2 star, etc., and then based on that I can find the answer. Okay. We will go through numerical examples, that is just one part. If my length of my duct is exactly equal to L star, then that is the simplest case you can ever have. I have a duct, f and dh are given, and I am going to say some m1 less than 1, and I am going to say this length L equal to L star. If I have this case, then I am going to say fully it is going to become m equal to 1 at that exit. Simplest case, really think about it. For this L equal to L1 star, I should say. For this Mach number M1, this is the length needed, and I am providing exactly that length, and so it is just going to reach there. Okay, that is one simple case where I will have M2 equal to 1 here. Okay. Now the next case is if I have again M1 subsonic, but I am having a length greater than, I will call this again L, while my L star is still the same. This is my L1 star. L1 star ends there from the starting point. If I think of it that way, now I have more length. What will the flow do? It will decrease, it will send out extra compression waves from this excess length, such that those compression waves go, and it is subsonic, so it will go faster, it will go reach this point. We are thinking only steady state as of now. So all that compression waves will go ahead and make this flow come slower into it. So M1 will now change to M1 prime, which will be less than M1 value, okay, such that it is equivalent to thinking about, let us say I will pick this problem. Okay. It is equivalent to thinking about, I am having a case where this length is extended more here, such that I have a M1 prime here, M1 prime more in this side, and now that will be equal to that M1 prime giving L1 star, L1 prime star, let us say. It is going from this M1 prime to L1 prime star, that will be equal to your new L. That is how this problem goes at that point. It will decrease it such that that will happen. Now the next thing, I will do the whole thing for supersonic. It is a little different in supersonic. Simple cases are exactly the same. M1 greater than 1, this is my L star, L1 star, and this is my L if I think about M2 greater than 1. Okay, it is just decreasing from M1 towards M1 M exit equal to 1, but before that we stopped the duct. So it is not exactly equal to 1, it is slightly greater than 1. It is decreasing monotonically towards that. That is the simplest case, similar to subsonic case. If I make this equal to L1 star, then also it is simple case, exit will be M equal to 1. Now we will go for the more than that length case. Say I am just slightly more than that L star case. If I have this case, then typically there will be a shock. By the way, it will be ahead of this L1 star value, that location. Okay, the shock will always be ahead of this. What is the rationale for that? This extra length is what is going to cause excess resistance, and so that will send out a set of compression waves, and as they come in, they find higher and higher Mach number flow resisting it. So there will be a point where those set of compression waves coming to an equilibrium against the flow. It is like treadmill, right? Shock wants to run ahead and flow is going this way, and it will come and stabilize somewhere here typically. Okay. So there will be a shock sitting here. Here it is subsonic flow. Now I will call this as my M2, M1, M2, M2 prime I will call this. Okay, the just downstream of the shock, immediate downstream of the shock. This is less than 1, and after that it takes the subsonic path. We discussed this on the plot that day, because in the subsonic section for F L star by D versus Mach number, we found that in subsonic region L star can be much higher. Okay. So instead of going the supersonic way where the L star is only this length, instead of this it takes a subsonic solution where it has higher length. Okay, that is the idea. For the same F and D, this curve will just become like L star curve. It has higher L star. Okay, so it jumps there. That is the idea behind this going to the subsonic side. After that, it will still want to reach m equal to 1 at the exit. This will be the case. Okay. If I keep on extending this length, then we will go to a situation where the shock goes more and more upstream. If I extend it any further, then the shock will go sit outside this duct, After that, if I look at what is the flow inside the duct, it is only subsonic flow. I will go back to the other board here and the problem just becomes this. Of course, there may be a shock sitting in front of it, and before that there could be a supersonic flow even here. I am not showing you that part here, that is all it should be. Okay. With this idea, I just wanted to reiterate this whole thing in one sequence. Okay. What if I start with m equal to 1 in here, m1 equal to 1? I cannot send a m1 equal to 1 flow into any duct, okay, because immediately after that there is a friction which will send compression waves, which will slow down the flow, and immediately you will get only the subsonic case behind it. That is why transonic problem is very, very difficult. Okay, if it becomes m equal to 1, immediately it forms a shock and decreases the Mach number immediately after that, okay, and you will suddenly have lower flow rates. Okay. That is the way it goes. Now we will go pick a numerical example. I will deal with only gamma equal to 1.4. Typically air is what I am considering as my fluid, okay, and I am having a simple case. I will consider this as problem A, where I am having a duct with F equal to 0.002, hydraulic diameter given to be 5 centimeters, 0.05 mm, 0.05 meters, and L is given to be 2 meters. I am having m1 equal to 0.2 Mach number. I want to find what is the exit Mach number. Okay, that is the idea. To start with this problem, always if it is a friction problem, immediately I want to find L star, because based on L versus L star, whether L is less than or greater than my L star, my approach to the problem changes. So first thing I need to do is find L star. Okay. So m1 equal to 0.2 from tables, gamma equal to 1.4 tables. If I go look at it, 4f L star by dh is given to be 14.533. Okay. So based on f and dh given for my friction factor for my particular duct, I am going to get L star as 90.83 meters. Okay. Now the numbers look ridiculous, right? L is 2 meter and L star is 90 meters. Only when it goes 90 meters long, my Mach number will ever reach m equal to 1. I am starting with very, very low Mach number. That is why this case is happening. If I had started with 0.9, it may not be very long. It may be just 2 meters or so. Okay. You remember the curve that was looking, I actually have the curve in this board. The curve is looking like this, and Mach 0.2 is somewhere way high out there. That is why it is looking like this. Okay. The numbers may look ridiculous at the beginning. We will know it immediately. Okay. If this is the case, what should I do? I just have to go and draw some dotted line and L star somewhere out there. This will become L2 star, where this is my m2. So this is the remaining length. I know this is 2 meters. From m1, from the inlet to the star is L1 star, that is given here. I will make it L1 star, and this is my L2 star. So L equal to L2 star minus L1 star, which means I can find my L2 star. Okay. L2 star value is 88.83 meters. So I will go and find 4FL by D, 4F L2 star by DH. That comes out to be 14.213 meters. Previously it was 14.533 for m equal to 0.2. From there it has become slightly lesser, that is Mach number increased a little bit, that is what we have. From here, I should not be putting meters here, it is not meters, sorry, okay, no units, it is non dimensional, L by D. Okay. So, from here I am going to find my Mach number M2. This will give me a M2 of 0.208. Okay. If you look at it, it has changed only from 0.20 to 0.208, because this length is far small compared to my L1 star that I have here. L is 2 meters, L1 star is 90 meters, it is not that much of a change when I look at the overall needed length. Okay. So, there is not much of change. So, this is the first problem. Let us pick some other length, let us say L equal to 45 meters, the same problem as before. I just want to see what if I go halfway to L1 star roughly. Okay. So, since I know the problem, I will just go through the same process, nothing changes. I know that length is less than L1 star. So, if I go through this one, L2 star is 45.83 meters. So, 4f L2 star by dh is going to be 0.265. Oh, sorry, I jumped. 0.265 is my Mach number. This comes out to be 7.33. 333. Okay. And this gives me a Mach number of 0.265. You still find that even if I go halfway through to L star, it has not gone too much away from Mach 0.2. Okay. This is the idea of this particular curve. I will go back to this curve. I am having 4f L star by d versus Mach number. This curve is very steep at the beginning and then it turns to become shallow. Only when it is shallow there will be too much change in Mach number. Till that time the change is only in L star, L basically. Okay, the change is mainly in the length of the duct, not much change in M. That is what is currently happening. Okay. So, when you get an answer like this, you should think about whether it is ridiculous or not. Currently it is not, so you can live with this particular problem. Okay. Now, I will change the problem in another way. I do not want to solve it in Mach number domain. Suddenly I want to solve the problem by saying how much length should I have so that my pressure at the exit is half of pressure at the inlet. Okay, I am changing the problem. I am going to say I am having a duct AF and DH are given for my tube. I am going to say there is some M1, let us say it is again 0.2 and I am given some P1. I want to know what should be the length L such that P2 equal to half of P1. This is the problem I want to solve. Okay. So, how will I approach the problem? It is not very difficult. I am again going to say for this M1 I know my L1 star. From problem A I know the L1 star, it is 90.83 meters. I know this number. Now, the only thing I have to think about is what should be my Mach number such that I will get half the pressure. Is it very difficult to do? It is not very difficult to do, but you have to just look through that problem. Okay. It so happens that there is another column called P by P star given in your tables. Okay. If you have that, it is easy. Otherwise, it is a little more complicated to solve this problem. It so happens that in my tables I have it, so we will just use this directly for this example. Okay. P2 by P star we know is equal to P1 by P star. It looks like I am switching star up and down, just keep it as up for now. Okay. So, we know this because P star is going to be the same whatever if my initial condition is fixed. Okay. So, I am going to end up with this, I am going to say this is equal to 2.728. Okay. That is, I already divided by 2 to get to this answer, I am having this answer. Okay. Now, this from my tables gamma equal to 1.4 and this P by P star will give me my M2 as 0.396. This is the value I get. Now, my actual objective is to find the length of the duct. So, what should I do? I have to go and find L2 star again from there. So, from my tables again for this Mach number, my L2 star, actually what we will get from tables is 4f L star etc. So, if my L2 star will be, actually I will put 4f by dh, this number will be 2.388. Okay. So, from here I will find my L2 star. L2 star happens to be 14.925 meters. Okay. Think about this, when I started with m equal to 0.2, my number was 90 meters. When it became roughly 0.4, I have only 14.9 meters. Okay. So, the curve is starting to turn, that particular curve here. This particular curve is starting to turn around 0.3 plus, it will start to turn steeply. Okay. Initially it was out there, now it is slowly turning. That turning point starts seriously only after 0.3 Mach number. Above 0.3 Mach number, there is more sensitivity to Mach number. And when you are going very close to m equal to 1, there is a lot more change to it. Okay. So, we know that from here my star value is 90 meters away, and from this point my star value is only 14.9 meters away. So, the difference must be my L. Okay. L happens to be 90.83 minus 14. I will make it 14.93 because it gives me nice number. 75.9 meters is the distance I need to extend this duct before it goes to half the pressure at the inlet. Okay. That is the current situation we will have. Okay. That is the idea of that particular problem. Now, we still did not do a case where I have a subsonic entry and my length is more than L star. So, we will pick a case where I have a subsonic entry and my length is more than L star. Let us say I have only 100 meters. 100 is a very nice number, slightly above 90. So, I will just pick 100. So, I am going to say my L equal to 100 meters, M1 equal to 0.2, which gives my L1 star is equal to 91.83 meters. These are the numbers we have. Now, we know that 90.83 meters. Okay. We know that now there will be compression waves traveling upstream and adjusting this M1 to M1 prime. I do not know what value it is, but I know my M2, the exit of my duct, will be m equal to 1. Okay. So, it will be getting adjusted to some M1 prime, and what will it get adjusted to? M1 prime will now have a L star of 100, that is how it will get adjusted. So, now all I have to do is 4f into 100 divided by dh. If I do this, of course I am still using the same f and same dh for all my problems. If I use that, it will be 4 into 0.002 into 100 divided by 0.05 meters. This number comes out to be 16. So, my M1 prime comes out to be 0.193. Okay. So, I started it with 0.2, but since the length is more than this length, the flow immediately got adjusted to m at the inlet happens to be 0.193, and after that it is just a simple fan of flow, the condition where it is just choked. At the exit it is m equal to 1, very nice problem. So it just goes slowly increasing Mach number and eventually it will go to a point where it is m equal to 1. If you want to find any other variable, I am sure you can find out. So I am just going to go to supersonic cases from now on. Okay. Of course I can now tell that find the temperature at some location, or tell me when the temperature goes triple the initial temperature, all those kind of problems we can solve. Okay. I am just avoiding those, you know, you can calculate it. Actually temperature decreases from subsonic to m equal to 1, so temperature should go 1/3 of if I want to ask a question. So now we will look at supersonic inlet. I will just start here. So I am going to say that is all subsonic cases, and this I believe was problem D, A, B, and this was problem C. I just did not number them. Now we will go for next problem. I will call this 2A. Now I am going to say M1 is 2.0 instead of 0.2, same F, same DH. Just for simplicity I did not want to change these numbers. Of course I will give you another exercise with this, with all these numbers varying. Not very difficult to calculate, but it is just something you got to get used to. These numbers you can make a mistake. Typically in looking up tables, the gamma can be different in different books. Some books will give you so many gamma values, different tables for each gamma value. Should not be looking at the wrong gamma value, you will get all wrong results. Typically the mistake made by most students. So I will pick a case. I am being careful and I am going to say L equal to 1.5 meters. Previously we had case A was L equal to 2 meters. I am picking 1.5 meters here. You will see why in a minute. I already calculated some things. Okay. M1 equal to 2. If I start here, of course the very first thing I want to find the Mach number at the exit. That is the overall objective of my problem. Now to find that, of course I have to know how close to m equal to 1 am I at the exit. So I will first find L star, L1 star. Okay. If I find 4f L1 star by dh for this Mach number, for that gamma equal to 1.4, I am going to get a number 0.305, which is going to give me L1 star as 1.906 meters. This is the reason I did not choose 2 meters, okay, because I already calculated this once before coming to class. Okay. You are finding that now I have chosen a case L less than L1 star, which is very simple now. It is supersonic, it will end with supersonic, but lesser Mach number than the initial. Okay. Similar thing I need to do. Now I will just find that it has 0.406 meters from this point to L star. That is the distance it has. So I have to find L2 star happens to be 0.406 meters. If this is 0.406 meters, I just have to find 4f L2 star by dh, okay, and 4f L2 star by dh for that f and dh given happens to be 0.065. Okay. Now I have to go to gamma equal to 1.4 tables, look for where this occurs in that table and choose that Mach number. That Mach number comes out to be 1.30. I started with Mach 2 and I am ending with 1.3 Mach, and within that 0.4 meters left it is going to go to m equal to 1. Okay, that is what we are seeing. Here you are seeing that there is a lot of sensitivity to length in terms of Mach number change. Okay. For a small length change, Mach number changes a lot. That is about supersonic cases. Now we will choose a case where L is greater than L star. Now I will choose L greater than L star. So I am going to pick L equal to 3. Same M equal to 2.0 as my Mach number. I am picking L equal to 3 meters. So we expect a shock. Let us say this was my L1 star. I am going past that point and M equal to 2.0 is the beginning. Now I know my shock should be sitting slightly inside of this. I told you already. So I am expecting a shock somewhere here, and I am going to say Mach number before is M2, Mach number after is M2 prime, just after the shock. Shock is happening at that infinitesimally thin location. Okay. So I want to find that particular length at which the shock occurs. I will call this as location of shock LS, okay, length at which shock occurs, okay, such that I will get M3 equal to 1. That is the overall thing. I am just doing Mach number variation in a shock in my tube. Of course, I know that once I know Mach number distribution in my tube, I can find any other property because I have fan out flow tables with me. Okay. For a given Mach number, I can just go and find any other property. If I want to find, say, somewhere in the middle, I can just go and calculate from M2 prime. I went so much downstream with this F and DH, I can solve that problem. It is not very difficult to solve. And if I want P by P star, whatever, I can get every number. So I can change pressures also across. So I am not solving those, but I will probably give you those as exercise problems. Okay. So how will I solve this? So I am going to first treat this part of the problem as supersonic flow going some length less than L star, which is just now we did the problem A of second 2A, right? That was this problem, and this is up 2B. I keep forgetting to label these problems. This is 2B, and so I will solve this as if it is 2A. After that, I have a normal shock problem. I will just go to normal shock tables and jump from here to here across this. Once I do this from here to here, remaining portion, now I have to see if I get this Mach number to be 1 at the exit. So I will again solve this as my 1A problem, and I will see if this matches. How will I check that? Simplest way to check, what if it is more than length of this particular M2 star, M2 prime star. If that is the case, so all I need to do is find the remaining length and see if that is more than L star corresponding to M2 prime. That is all I need to do. If it is equal to that L star, then I have solved my problem. Okay. So I have to go through some iterations here. I cannot directly guess what my LS will be. So I have to go through a set of iterations. I have gone through the iterations, so I will just give it to you. I will just tell you how it works. I am going to have a full column LS, L1 star minus LS, 4F by DH times L1 star minus LS, and that is going to give me my M2. Just to be clear, I have written this LS, L1 minus L1 star minus LS, that happens to be my L2 star really. If you go and look at problem 2A, that is what was our L2 star. Now I will say L4F L2 star by DH. From here I will go read up my M2 from there. Once I know M2, I will go to normal shock tables and find M2 prime from there. From there I will go to 4F by DH times L2 prime star. From this Mach number I will go to fan out flow tables, find this. Of course, now you have to pick only subsonic solution. Okay, I will pick the subsonic solution from here, and from here I will get a L2 prime star. I will just have to multiply appropriately DH by 4F, you will get that. After all this, Finally, I have to check whether this distance is more than or less than my that L2 prime star. So, the way I want to do it, I will find the L2 prime star, that will be distance from this shock till where m equal to 1 occurs, okay. That plus this Ls must be equal to my full duct length. So, I will do it that way. I am going to say I have Ls plus L2 prime star as my last column. I want to make this last column equal to L, my 3 meters. That is the overall objective of my solving this. That is my iterative process. So, now I am going to pick, let us say 1.3, because I already have answer for 1.3. 1.30 I am picking. Okay. If I pick 1.30, we can get numbers, okay, and I said that L1 star was 1.906 meters, okay. So, I can get the L1 star minus Ls, that will be 0.606 meters. From here I am going to get 4f L2 star by dh, that number happens to be 0.097. From this I can back calculate, I can go to my fan flow tables, get a Mach number for gamma equal to 1.4, 1.393 is my Mach number, and m2 prime I am now going to normal shock tables across these two columns alone, 0.743. Again remember, normal shock tables, when you are flipping pages you should go to the correct gamma tables. Okay. Now I will go back to fan flow tables from here to the next one, that number is 0.137. From here I will calculate my L2 star, 0.856. Now I have to add Ls plus L2 star, that comes out to be 2.156 meters. So, I am finding that when my shock is here, my duct becomes m equal to 1 somewhere here itself, that is what I find in this case. If this is where it becomes m equal to 1 and I have extra length, what will happen? There will be more compression waves generated and it will go upstream and push this shock further upstream. So, my logical way to go is, now I have to decrease my Ls. Okay. So, I will go decrease my Ls, I will make it 1.0. I initially, when I iterate, I pick always nice numbers. Okay. Eventually, when we are getting closer to the answer, we will think about something else. So, from here 1 minus 1.906 minus 1 is 0.906. From here I will write the next number, 0.145, and now this, if I go to tables, I do not get exact number, I have to interpolate. So, I will just pick a rough estimate of the order of 1.52. I just picked the closest one in the interpolate. Okay. From here I go to normal shock tables across here, 0.694. Now I go from here to fan flow tables and get the next number, 0.220, which will give me my L2 star as 1.375. So, my Ls plus L2 star is 2.375 meters. That is what I have finally, 2.375. So, of course, yes, 2.15 became 2.375, still not enough, my shock has to go further upstream. So, I will change more drastically, I will make it 0.5. 0.5 meters, it has gone well ahead now. Okay. 0.5 meters, I will go through the same process, 1.406 meters. 4FL by D will give me 0.225. M2 is approximately 1.75 Mach number. From there, normal shock tables gives me 0.628 Mach number. downstream of the shock. From here I go back to fan of flow subsonic solution, gamma equal to 1.4, I am going to get 0.391. From there I can calculate L2 star 2.444, and that gives me 2.944 meters, getting close to the answer. Okay. So, I still have to go further upstream, but I am close to the answer. So, now I will start changing slowly. I will go to 0.40, 0.40, that number is 1.506 meters, that I do 4FL by D 0.241, and this is approximately 1.80. Till now I am doing only approximately, I will do the more better at interpolation at the last step. Okay. The next is across my normal shock, that number is 0.616. Okay. After that I do 4FL by D 0.431, which will give me my L2 star as 2.694, which now has crossed 3.094 meters. So, now I find that if I put my shock at 0.4 meters from inlet, I am going to have Mach 1 slightly downstream of this exit, which means now my answer is between the last two iterations. Okay. So, now I will do more careful iteration. Okay. From now onwards I will not do this approximate stuff, I will try and do correct interpolation and everything. I will pick, of course I want to pick the midpoint, okay, 0.45, I will pick the midpoint, that gives me 1.456, that gives me the next column 0.233. Now, from here I want to go find Mach number ahead of shock, that value now I will do it more carefully, 1.744, no more approximate methods, doing it a little more careful, 774, sorry, 774. Of course, the way I checked my answer was because 744 was not in between these two numbers. Okay, when you are iterating, just go through this simple checks. Okay, 774. Now I will go look at normal shock tables, and that gives me 0.623. From here I go back to fan of flow tables, 0.407, and that is giving me 2.544 meters. So, I am getting 2.994. Okay, of course, I can go one more iteration and try 0.46. Should I go down or up? 44 or so. I can try a 0.44 and I may get an answer even closer to 3. Okay, but I want to stop at this point, 2.994. I will stop. Okay, this is where it goes to at this point. Okay, this is the iterative procedure you have to follow to get to a problem solution of this type. Once I solved up to this point, this is the starting point if I want to know more properties. Okay. Now I know that my shock is sitting at 0.45 meters, up to there it is supersonic, after that it is all subsonic, that is what I figured out. After that, if I want to know the final exit pressure or my P naught at the exit, all those things I have to go through the calculation all the way, P naught 2 by P naught 2 star, etc. I have to go through and find out all these details. Okay. And remember that there is a P naught change across the shock also, you have to take that also into account. Yeah, of course, I am not doing that right now, I will give you another problem with pressure change. Okay. So, I think this will be our last numerical example, I will not give you any more of numerical examples. So, now this becomes here in 2C, I am starting with M1 equal to 2.0, same F, same DH. Now, I am telling I have that exact situation like in problem B, I am having length equal to 3 meters, okay, and we started with M1 equal to 2.0. So, we know my shock location is LS equal to 0.45 meters, maybe I am right, maybe it has to be 442 something. I will just assume it is 45 right now. Okay. I did not go through one more iteration to make it any more accurate. So, we will keep it as 0.45 meters. So, if the question is this, if P1 is equal to 25 bar, find P exit. That is my P exit. Find my P exit, that is the question I want to ask. Okay. It is easier to work with P0, so I will switch to P0 from here itself. I know P1 and I know M1, I can find P0. Where should I go? Isentropic tables. Gamma equal to 1.4, isentropic tables. Okay, there are so many tables in compressible flow tables books. So, you have to choose the correct table and correct gamma value. Okay. So, now I will go find P01, that will be 25 divided by P by P naught for m equal to 2, that is 0.128, that gives me 195 bar. Okay. 195 bar. Of course, I could work through with just P by P star all through, but I just wanted to work with P0 by P0 star just for the fun of it. Okay. So, now I want to find, we know this is my P01, we will keep this. Now, I look at shock. Okay. We know the shock Mach number, right, from the previous problem. We know that the shock Mach number is 1.774. 1.774. So, I will go and find that value, P02 prime by P02, okay, P02 prime by P02, we labeled this as 2, this as 2 prime, and then I have exit. These are the values I have. Okay. P02 by P02 prime, I did not write that value, it looks like 0.824. I have this number. Okay. So, I want to find what will be the P0 star at this point. Okay. By the way, since it is all subsonic flow here, P0 star here is same as P0 star here, right. P0 star does not change, P0 star will be the same value, and we know that at the exit m equal to 1. So, P0 here is equal to P0 star. Okay. So, all I need to do is track P0 only up to here, that is enough. Of course, if I started with working with P star, then I have to track only P star up to here, and that will be the pressure at the exit. I wanted to take a longer path. Okay. So, now actually I want to find P02 by P01. Okay. P02 by P01 is equal to P02 by P0 star into P0 star by P01. I told you gas dynamics people like ratios multiplying each other. Okay. So, this is equivalent to, I am in my tables it is given as P0 by P0 star. So, I will go find at M2 what is this value, divide that with M1 what is that value, okay, and that comes out to be 1.412 divided by 1.687, that value is 0.837. Okay. So, now look at these numbers, P02 prime by P02 I have P02 by P01, only thing left is P02 prime divided by P02 star, P0 prime star, okay, downstream star value. So, I just have to find that value, P02 prime divided by P0 star prime, that value happens to be 1.163. Now, if I multiply all these appropriately, I can get P0 star prime divided by P01. Okay. That is what you need to do. I will just do that right here, P0 star prime by P01. So, of course, I will take reciprocal of this, 1 by 1.163. So now I have P02 prime at the denominator. I go multiply it with this, okay. I will get P02 at the denominator. It comes out to be 0.824, and I will take this number, then I will have P01 at the denominator, which is what I want. So I multiply it with this 0.837. Okay. I actually did not find the number for this, I just used this. I know P01 is given to be 195 bar, we calculated. So I am going to multiply this ratio with P01 value to get P0 star prime. Okay. P0 star prime happens to be 115.6 bar. Okay. Now from here, of course, I can go to isentropic tables and find m equal to 1, what will be the p value. That comes out to be p at exit happens to be 0.528 of that, you should know gamma equal to 1.4 is 0.528 is the ratio, that comes out to be 61 bar. This is what I end up with. Now of course it looks like I went through a little bit longer path because it is P naught. I wanted to solve a problem in class with P naught variation, so I went through this. I could have solved it with P star, then I would have avoided going to my isentropic tables completely. That is the only difference. Okay. Now I started with 25 bar and I am ending with 61 bar. Is that logical? Flow is going from low pressure to high pressure, it looks like. Is that right? It happens to be correct. What will be the reason I will give? My momentum is decreasing. Okay. I am going from m equal to 2 to m equal to 1 finally. Okay. That is why it is matching. Otherwise, the flow will never go from low pressure to high pressure. Think about it. Okay. But I had other energy, not just pressure energy. I had other energy also in here, momentum or kinetic energy I had, excess of it, and that is now decreasing, and that is becoming pressure energy during the process. Okay. That is what has happened eventually. Okay. I will probably show some animation tomorrow. If not, we will just start heat transfer into the duct and what happens to gas dynamics during that inside the duct. That we will start with tomorrow. See you people next class.